Hi, I'm Andy. I'm going to talk about merge on read in Apache Hudi. I'll show you some examples for how it helps, explain how it works under the hood, and then show you a quick demo of how you can actually use it in action. So Apache Hudi has two table types. You have copy on write, which is great for your basic append-only workloads like telemetry, and you have merge on read, which can give you incredible performance gains when you're working with mutable workloads that involve updating data in your tables. Now, let's talk about why merge on read exists. Object storage is immutable, and that means updating data in object storage is expensive. Under the hood, Hudi stores your data in files, and when you want to update those files, you have to actually rewrite the data, which can be costly in your I/O and the compute involved in actually processing and writing that data. So, why does mutable data even matter on the Lighthouse? We know Apache Hudi was created at Uber, so let's talk about a rideshare problem that's near and dear to Uber. Now, this isn't necessarily exactly what they face, but you could imagine this as a hypothetical scenario. So, imagine a driver completes a ride. That ride gets written to the Hudi Lake House. After the rider leaves a tip, and that tip also gets updated in the lake house because Uber needs to know what they should pay the driver. At the end of the day, they have all of these updates, including more rides, they have tips, and they have changes that need to be put in place before they can calculate how much to pay the driver. Now, the tip isn't the only thing that can change. In a ride, there's a lot of real world scenarios that happen. Like you might actually pass tolls that need to be added to the end tally, or maybe the rider brought their best friend in the car and the best friend made a mess, so you have a cleaning fee. All of these things can make updates necessary in the database. And when you're working with real world data, typically you will have to deal with updates at some point. Now, let's take a look under the hood at how merge on read and copy on write actually function in Hudi. We'll start with understanding how copy on write works. Here you have some incoming updates. Imagine these are new records that are being updated in the Hudi table. Your writer then writes these to Parquet files. So the log one here is a Parquet file. It's the columnar format that stores the data in Hudi. And then, of course, your reader, an engine like Apache Spark, will read the latest data file. And it knows what to read from the Hudi timeline or the Hudi metadata table if you're using that. So with these updates that are coming in, the writer will directly write them to Parquet. So they come in and immediately you write a new Parquet file. We'll call this version 2. And then the reader knows to read version 2. Now, after some time, the cleaner will go in and clean up version 1, and that file will get deleted. Now, when more updates come in, they'll come in, we'll do the same thing. It'll create a new version. You'll have version 3, and the reader will point at version 3, and then eventually version 2 will get cleaned up. Now, the challenge here is that you keep rewriting these Parquet files. And in a Parquet file, you might have thousands or even millions of records. Whereas even a few updates coming in will require you to go and rewrite all of those records. That becomes expensive, especially if you're rewriting the same Parquet file over and over. That's where merge on read comes in. With merge on read, you'll have those incoming updates. But instead of directly writing to the Parquet file, the writer will actually add these as log files. The log files are stored in the Avro format, so row based, instead of in Parquet, and they're attached to the Parquet file. We call this whole thing here the base file plus the log files. We call that a file group, and that'll have its own ID, so you can actually query a file group. Now, the reader, our engine, like I mentioned, could be Apache Spark, for example, or another engine like Trino, will be able to read this. Now, when you read it, there's actually two different views that you can have. You can have a read optimized view, which is denoted by RO, or you can have a real-time view, which is denoted by RT. And these are views in your data catalog. So let's start with the read optimized view. When you do the read optimized view, it's meant for fast read. So it will only query the Parquet file. You won't read all of the Avro log files. Now, when you have a real-time view, the reader will actually compact all of the log files and it will read that entire latest file group. So that allows you to get the latest state of the table in real time. The query might take a little bit longer though, because it needs to not only read the Parquet, but also merge those log files in on the fly. Now, the other key piece is compaction. Compaction is a service that can run either synchronously or asynchronously to merge those log files into Parquet files. So this is how merge on read works. Instead of directly rewriting the Parquet files, you might wait for some more log files to accumulate. So we have more writes. Now we've got a bunch of log files in our base Parquet file. What happens here is we merge those into a new Parquet file. So we have version 2 here, and then our reader will point at the latest version. And similar to copy on write, eventually the cleaner service will clean up the older version. As we have more updates coming in, the same thing will happen. We'll add the log files to the new file group, which is version 2. And eventually, when compaction runs, those log files will get merged into a new base Parquet file. Each of these we call file slices. So a file slice is the state of a file group at a specific instance. And you can think of it as a version snapshot. The whole purpose of this is to help efficiently reconstruct the table state if you want to do a snapshot query to understand the state of a table in time. A snapshot will consist in a merge on read table as the base file plus all the log files at that instant. And that's basically it for merge on read and copy on write. Let's look at a real example using the Onehouse UI. This is an Apache Hudi table that I've created in Onehouse by ingesting some data. We can see here that there's data constantly writing to this table. It's a merge on read table, so I know that when I have updates, I'll get those log files. Now, if I go into my related resources, I've set up a managed compaction service on this table, which will automatically compact the log files for me. This is a feature that Onehouse offers. I can look at my table history, and I see here that I had a compaction. So this would have compacted all the log files. And then since then, I had 2 commits. We can look in and see that this commit contains some updates. That would create log files. Now I can go to my compaction backlog to see how many log files I have that need to be compacted. And it shows me this file group in a specific partition has 1 log file that needs to be compacted. So when compaction runs, this will go and be merged into the base Parquet file.